And I'm definitely going to, oh, okay, so does everybody see the screen? Everything's good, I hope.
Yeah.
Just, okay, great. Okay, so now this was, it didn't take you too long, hopefully. And like I said, thank you all for submitting your assignments. I looked over them. Like I said, I don't want to correct them because I'd rather you guys take it step by step and see where you might have gone wrong. And I will make a few comments as I'm correcting it because I did have a cursory look at all your assignments. I mean, overall, they were done very well. No problem there. But so this was a problem, okay? And and so this was a problem. And as I said, what you do is that all this information here that you see here, all of this here, this basically all comes from the architect. He's going to decide how he's going to be making his envelope. In other words, how his roof assembly is going to be put together. So he would send you his architectural drawings, and this would be all listed. And architects have this tendency to always, like when they're indicating something, they will always start, from the top and then list everything that they want to put to make their envelope. And then after that, you would take this information here, and of course, you would have to try to quantify what each one of these would impose on your structure. And you, as a designer of a structure, would have to choose this here, the steel deck, because that is one of the structural components that carries all of this. And then the second most important component, of course, is the open web steel joist, and then so on and so on. So that's what you would do. Uh, so like I said, so the dead load, you would go to 3-ply asphalt and gravel. Okay, so like I said, if you refer to that sheet that I provided you with, that's a pretty good sheet. It covers most of these situations. If ever you don't find it exactly in the sheet, or if ever you can't, like, extrapolate or interpolate the values from the sheet, you can always go on the internet, okay, and find what the things might weigh. And ultimately, if you can't find anything, well, be conservative and put something heavier than you think it's going to actually weigh. So here I had the 3-ply asphalt engraved, and I had 0.27. And then going further down, I had 50 millimeters of residue insulation. The table I provided for you gives you a value per 100 millimeters of insulation. So therefore, I would take only half that value. And then as far as the gypsum board goes, the same thing. The table provides you with a value for 10, and therefore I, I kind of prorate this to 12.5, and that gives me the weight of gypsum board. And so this is approximately, like I said, this is approximately 2 pounds per square foot. So next time you guys go into a renovation center and you see gypsum boards that weigh 4 feet by 8 feet, so that's 32 square feet. And if it's half-inch thick, well, keep in mind that 32 times 2 is 64. That sheet's going to end up weighing about 64 pounds. So that's after the gypsum board, you have the steel deck, and here the table provides you with a value for the steel deck, okay? And if you go into some manufacturer's catalog, you can get something a little bit more accurate, but this is fairly good enough for what you need to do in order of estimating your dead loads. Then after that, this is assumed, and then once you design the joist, you just go back and verify if this is a reasonable value that you've assumed. So, but I find that 2 pounds per square foot is a reasonable amount for the open web steel joist. And after that, you have, of course, what you don't see there, but you're going to have to realize is that eventually, when this building is going to be finished, the mechanical engineer is going to have ducts in the ceiling. He's going to have pipes. He's going to have wiring and so on. The electrical engineer, there's going to be maybe a sprinkler system and so on and so on. So since you can't wait until that's all designed and know exactly where it's going to be and try to estimate that, you just make an allowance for it. And I think that 0.25 kPa is a reasonable amount, especially if it's not a heavy building in a sense. So that's a good amount. And then after that, the only thing you have to worry about is that finished ceiling that the architect wants to put in his building. And therefore, again, 16 millimeters prorated, and that comes out to 0.3. And you add it all up. And of course, 0.97 is not what you would actually use. You would tend to round this up to 1 kPa. And that's approximately 20 pounds per square foot. And that's a good ballpark figure for what the dead load on an industrial building should weigh. So, like for example, if you're going into a Costco or a warehouse store, and if you look up on the ceiling, you're going to see the open web steel joists, you're going to see the steel deck, you're going to see the mechanical equipment that's being supported, and so on and so on. And 20 pounds per square foot or 1 kPa is a reasonable amount. So I would even take that as being the minimum amount that I would design the roof for. Now, I just want to make one comment. I've had a couple of students, 2 to be exact, whereby they've included here, okay, the weight of partitions. Okay, weight of partitions. You don't apply a partitions to a roof. In other words, partitions are only walls that are put on a floor plan in order to divide the space into different rooms or different areas. So you do not put any partitions in addition to what you see here, okay? And really, the only thing that you have to really think about is what is the mechanical, okay, electrical that might be going in, and that's what you should be making allowance for. So that's the only comment I had. I think you all had approximately this value here, okay? So I'm glad that you guys were able to at least, do it fairly well. And hopefully now that you see what I've come up with. Now, this is my answer. If you guys came up with a number bigger than this, don't worry. That means you're being more conservative. If you came up with something less than this, then you should be concerned, because then you might have slightly underestimated your dead loads. So does anybody have any questions before, because that's all I need to say on the assignment. Does anybody have any questions before I move on to the lecture? Or is it all good?
Yeah, I have a question. So when do we add partitions then?
When you add partitions, you say? Yeah, the partitions are for floor plans. In other words, when you're inside the building. Okay. So in other words, if I have a ground floor, if I have a second floor or a third floor, inside the building is where you put partitions. In other words, that's where you would be putting walls up. Okay. And if you're designing for example, if you're designing an office building, 99% of the time, office buildings, they don't know who's going to be coming in. They don't know who's going to be renting the space. They don't know how the space is going to be subdivided. So for an office space, you tend to, well, it's not you tend to, for an office space, you have to allocate 1 kPa, 20 pounds per square foot for possible future partitions if there's none indicated by the architect on the floor. And that's for office buildings and so on. For residential, I find 1 kPa is a lot for a residential area, because I don't say, and I tend to, for a residential area, this is my own guesstimate, I tend to allow about 0.5 kPa for residential area. But for commercial spaces that don't have any partition, the code requires at least 1 kPa, okay? So it's only when you're doing the floor space that you worry about partition load, but not on roofs. On roofs, we will never put any partitions on the roof. Is that okay with everybody? Okay, so I'm going to stop sharing this. And now I'm going to talk about the lecture. Oops. Okay. Okay, so last week we talked about dead loads, and we talked about the live loads or the occupancy loads, and of course, like I said, and the occupancy loads that we have. Okay, we have that table in the National Building Code that specifies what the minimum amount What's the minimum amount of load that you should be putting on a floor space depending on how it's going to be used? And like I said, guys, that is minimal. It's not maximum. And if ever you come a situation that you think that whatever the code wants you to put down as a minimum, you don't feel it's good enough, feel free to make it bigger. And as a matter of fact, if all of a sudden you're doing something and you took the value from the National Building Code and something goes wrong, it won't exonerate you from being responsible. Yeah, you won't be blamed for not at least meeting the code, but it was up to you to judge whether or not that code requirement in your judgment was sufficient or not. And then you had to decide accordingly. So keep that in mind, okay? Now, in most cases, those loads are appropriate. As a matter of fact, I mean, 99% of the time or 95% of the time, everybody uses those loads when they're designing a building. But keep in mind, just because you use those loads, if something goes wrong, you're still going to have a problem. Now, of course, the other type of load that we tend to want to evaluate if we're going to be designing a building is a snow load. Okay, and that's why I talk about snow loads. And of course, here in Quebec, do we have a choice? No. So now, when it comes to snow loads, this is how the National Building Code calculates snow loads. So this equation here comes straight out of the National Building Code, okay? And I will go through it step by step, and then we'll be doing examples. So the specified snow load, okay, is equal to the importance factor times the ground snow load factor times these factors here times the associated rain, okay? Now, the importance factor for snow. Like we talked about importance factors last week when we were talking about buildings, but now we'll just talk about the snow, okay? So when it comes to snow, okay, we'll talk, and then of course, this is the 1 in 50 year ground snow load. So in other words, what this is, I'll talk about this when we get into this a little bit more detail, but 1 in 50 means it's the probability of this amount of snow occurring one in the probability of 1 in 50 years. It doesn't mean that if it occurs today, it won't occur next year because it's already occurred today. It doesn't mean that it's going to be once every 50 years. It happens on the average once every 50 years. They can be back to back. In other words, 1 year after the other, but when they've accumulated the data, they found that the one that they use within a 50-year period, this is the one that they found was the maximum value, and that's how they came up with that 1 to 50. So this just the probability of it happening, it happened once every 50 years, the value that they put here. Now, CB is a basic roof snow load factor. We'll talk about this, okay, that's CB. And then you have CW, wind exposure factor, and I will talk about this, okay, and I'll tell you what you shouldn't do, okay, even though the code allows you to do certain things. And CS is a slope factor. You can appreciate that, like the slope of a roof will have an effect on how much snow can accumulate. And CA is a shape factor. So what happens is that, okay, not all roofs have a very uniform load depending on what's obstructing the snow or how the roof is shaped. It can have a non-uniform, and then this is what this allows for. It allows you to calculate what that call it accumulation, or that shape that can accumulate on your roof can come out to weigh. And we will talk about this for a very particular situation. And the SR of 1 in 50, okay, KPA. Oh yeah, the SR is the associated rain factor. Now guys, here, just to let you know, okay, they don't actually measure the rain in the wintertime. This number that you're gonna see eventually in the tables, this has been kind of guesstimated. It hasn't been actually measured. So this is just the rain that can occur during the winter. This is not the rain that occurs in the summertime, because there is another value in the table for the rain that occurs in the summertime. So now, the importance categories for buildings are based on the intent and use of an occupancy. And I think we talked about this last week, but just it doesn't hurt to repeat it. Okay, so you have basically what they call a low importance, buildings that represent a low hazard to human life in the event of a failure. Now, if you want to know what, okay, if you want to know what they mean by represents a low hazard, if you're going to have one occupant over 40 square meters, in other words, 400 square feet. If you have less than one occupant over 40 square meters, you can start considering it to be a low hazard building, okay? And that's why when people design barns, they realize it's only going to be the farmer that's going to be in the barn, and therefore it's going to be one person over God knows how many square meters, and therefore you can consider it to be low. But I never use this anyways. I don't care if the code allows me to do it. I'd rather have my structure being safe, and therefore I never even bother with this. Number two, of course, all buildings except low, high. In other words, this here normal would be your house, shopping center, office buildings, okay? These are all normal buildings, industrial buildings. And then, of course, high are buildings that are likely to be used as post-disaster shelters, such as schools and community centers. So therefore your CLSCs, no, maybe not CLSC, probably is under high because it's almost like a hospital, but your schools and so on, that would be a high. And then, of course, you have the post-disasters. And these are the buildings that you definitely want to stay up if ever there's a big disaster. In other words, you have an excessive amount of whatever it is that nature throws. And you want to make sure that the fire stations stay up so that the first responders can come out and help you. And you want to make sure that the hospitals stay up and so on. And you want to make sure that the buildings where the television and the radio stations are set up so that they can communicate with the people can stay up. You want to make sure that the power plants stay up. So these are all post-disaster buildings. And of course, this is that they would be designed for these for these importance factors. And then of course the values, okay? The values are here. So for example, what this means is that when I have a normal building, I don't have to increase my snow load. I just take a value of 1. If I start having a high, I have to increase it by 15%. And if I have a post-disaster, I increase my snow load by another 25%. And I put 25% more snow into the calculation of my structure. Now, for serviceability, this is, for example, I want to talk about serviceability. Like, for example, if ever you're calculating the deflections and the vibrations and so on, this is where this comes into play, serviceability. But for when you're designing for strength, these are your importance factors. And next year, in the design courses, you'll learn how to apply these for the design of wood structures, steel structures, and so on. Okay, we'll do that next year. So, any questions on this so far? Is everybody clear on this?
Yeah.
So, good? Okay. Thank you. Thank you. I'd like to get some kind of response, guys. Please all come in and say yes. I'd like to hear something. Now, the ground snow load SS and the associated road SR, okay? Well, that if you buy the National Building Code, if you want to spend over $200 and you buy the National Building Code, inside the National Building Code, there's an Appendix C. And the Appendix C has all the climatic, well, not all, it has climatic information for different areas of Canada, starting from starting from British Columbia all the way to Newfoundland. And then in each province, there's a certain amount of locations. Now, I didn't put all of them here because I would add maybe over 30, 40 pages. So I kind of scanned 3 pages for use, but you'll get to see how it works, okay? So this is, okay. Okay, let me get this out of my hair, okay? So if you go into the Appendix C, like I said, the very first page, you're going to start somewhere in BC, okay? And then you're going to have locations in BC listed, and then you're going to move over to Alberta, and then you're going to move over to Saskatchewan, and then over to Manitoba, Ontario, and then you're going to find Quebec. And then in Quebec, of course, all the towns called with A, like Actonville and so on, they would be listed alphabetically here, okay? And so, for example, we live in Montreal. So for example, if you want to know the climatic information with regards to Montreal, well, you would have it all on this line here, okay? Now, what they've done here is, for example, elevations in meters. So if you guys want to know like how high is Montreal above the sea level, well, Montreal is about 35 meters above the sea level, okay? And that's why the St. Lawrence River can actually flow out to the ocean, okay? Now, this here, design temperatures, if you want to know how cold it is, okay, well, this gives you an idea of how cold it is. So if ever you're looking for a place in Canada and you want to find where it's the warmest, you just come here and you go through each page in Appendix C and find the one that's got the, the best, and that's going to tell you where it's probably the warmest place to stay in Canada. I never bothered doing that. Okay, and then if you want to know how hot it gets in Canada, okay, this could tell you. Now, this information that you see here, we don't have, civil engineers aren't interested in this, okay, because this here is mostly for architects when they have to design their building envelopes, for mechanical engineers when they have to design the heating system or the air conditioning system. So this is all information that they would use in order to know how much insulation they need and how much heating is required, how much cooling is required, and so on and so on. So all this information here is it's very useful for the architects, very useful for the mechanical engineers, and so on. But as far as we're concerned, it makes no difference to us. This could be of interest to us because this tells us how much rain we get, okay? So for example, in Montreal, in the Montreal region, okay, within a 15-minute period, you can have, this tells you how many millimeters of rain that you might get in within a 15-minute period. So if ever you need to calculate some kind of flow for your pipes or whatever, okay, this tells you how much rain you can expect to get within 15 minutes, and then you'll know what is the capacity that your flow has to have based on the area that you're draining, and you'll be able to size your pipes. And I think that's something you're going to be doing in Mrs. Barbaruzzi's class. I'm not sure. Now, you can have the 1 in 15 minutes, okay, and then you can also worry about how much rain are you going to get in a day, because sometimes you might have to calculate the amount of rain in a day, because sometimes the architect might have a slow drain draining the roof, and therefore if you want to calculate how much water can get on the roof within one day, this might be of use for you. And then of course the annual precipitation, how much rain. So if you're looking for like if this is, like if you're looking for how much rain we get, you can appreciate that it seems to rain more in Lachute than it rains in Montreal, okay? Or there's more rain in Lachute, not rains more, there's more rain in Lachute. So this also can give you an idea. So here, if you go up in the, up north somewhere, see how little rain they get? That's because they probably get more snow because it's really cold up there. And the moisture index for us is not important, but for architects that are designing their envelope, it's very important, okay? And of course, total precipitation. Now, this is nothing to do with us because this is for architects if they want to know like how much pressure is going to be pushing into their envelope, so how watertight it has to be. So all of this is for the architects. This is what we would be interested in, okay? So this is what we're looking at, okay? Now you see here that 1 in 50 means that this is the recorded amounts that happened within a 50-year period or can occur once every 50 years. And therefore, if you want to know what the snow load is in Montreal, you can, and look, if you look down here, even for Montreal, what's interesting is that this is Montreal, 2.6 kPa. But then when you go out to Beaconsfield, which is still on the island of Montreal, they only have 2.3 kPa. If you go to Dorval, they have 2.4. And then if you go out to Outremont, they have 2.8. So even on the island of Montreal, okay, you can, have a different value of the ground snow load, okay? And what they do is they basically have monitoring stations all across Canada, and they collect the data from the snow that falls, and that's how they accumulate this information, okay? So this is the snow load. So therefore, if ever you want to calculate the snow load, the S value for Montreal, you would come to Montreal and you would take 2.6. And of course, the units are very important. This is in kPa. And of course, the associated rain, in other words, in Montreal, we know that it does rain in the winter time, and that rain will add to the weight of the snow. It will not remove it, and therefore will add another 0.4 kPa for the rain that can occur during the wintertime. This is not the rain that occurs in the summertime. Two totally different values. So this is just for that little bit of rain that can occur during the winter season. This is the actual rain that will occur during the summer, okay? Now here in Quebec, the snow load tends to govern the design of the roof, and therefore everybody just calculates snow load. But there's certain parts of Canada where it can rain as much as it can snow, and therefore you would have to check this load here for one case, and then you'd have to check this load here and see which is the one that's heavier to design your structure. In other words, would the rain load be heavier in the summertime than the snow load in the wintertime? And there in the other parts of Canada, you would have to do both checks and see which one is a higher, and that's the one you would use to design your roof. So that's one thing, at least in Quebec, we don't have to do. And then next week, we will be talking about this. This is the wind pressures. Now here they have 1 in 10. In other words, this used to be used before. We do not use this anymore. This means that this wind pressure here is going to occur or has occurred once every 10 years, or when they monitored all the readings over a 10-year period, this was the maximum value that they found. And then the same thing here. This was 1 in 50, the same that you have here. Okay, and of course, we won't get ever into this program. This is when you want to design for earthquake. So these are all the values for the earthquake loads that you have to evaluate, that you can use to evaluate the earthquake load on a building. So that gives you an overview. I mean, like, it's nice, you know, and what I find interesting is that there's a lot of information here that you can extrapolate, you know, by looking at it. And is anybody has any questions, or is it pretty clear? I mean, they made it simple, but does anybody have any questions?
No, all good.
It's all good. Thank you, Emmanuel. Okay, and like I said, we'll have a couple of examples. We'll come back and we'll use these tables, but just wanted to give you an idea what these things can be used for. Okay, so that's where you get those two values. Now, CB 0.8, like I think it was 2010, up to about 2010, CB was always 0.8, okay? That didn't change. But after 2010, or I believe it was 2005, guys, memory fails me right now, but I can tell you, if you go to an old building code, in other words, if you go to a National Building Code 2000, 1995, it's going to be, CB is always going to be 0.8. And they modified that later on, okay? Now, except for large roofs, they found that large roofs can have somewhat of a, you know, of a more of an accumulation that can occur on a large roof, and therefore, even though there's nothing that's going to obstruct the shape, and therefore they came up with a new way of calculating CB. Now, CB, okay, this is CB would be equal to this value here. In other words, 1.0 times 30 divided by LC squared, and that will become the value of CB. Okay, instead of 0.8, the value will become, but only when LC here, the characteristic length, is greater than 70 meters. Now, what's the characteristic length? Well, the characteristic length is, okay, LC is the characteristic length, and LC is 2W minus W squared over L. Okay, now what's W and L? Well, very simple. If you look, okay, W is the smaller plan dimension of the roof in meters, and of course use meters, and L is a larger planet. So it doesn't matter how the building is oriented, in which direction, whether it's north, south, east, west, okay? Just remember, okay, W is always the smaller of these two dimensions, and L is, and then of course, if you have a square roof, W and L are one and the same. So, and so that's what there's that. Now, people have asked, you know, like, what happens when you have an L-shaped building? Well, if you happen to have an L-shaped building, okay, if you happen to have an L-shaped building, well, this is the L-shaped building, let's say like this, and you take it like this, okay? So what you can do is you can assume that this is one rectangle, and you calculate the characteristic length. So this would be your W for this part of the roof, and this would be your L. And then you would calculate another one like here. This would be your W and that would be your L. And you would see which one gives you the biggest CB value. And that's what you would use to design your roof. Now, if they both happen to be under 70, then you don't have to worry about it. The minimum value you can use is 0.8. So don't worry about it, okay? So this only becomes important when this characteristic length, in other words, this here, exceeds 70. If it does not exceed 70, CB is always 0.8. So Yeah, it's only when you get into very big buildings, like in other words, warehouses, where you can have, very big buildings. I can tell you that it's when you start exceeding like 70 meters by 70 meters, that's when this thing will be a factor to worry about. Otherwise, it's usually always zero 0.8. But anyway, we're going to do the calculation to make sure that we can use zero 0.8. So that's CB, okay? And guys, the reason why they have a CB factor is because all the monitoring of the snow is being done on the floor, okay? And therefore, when it falls on the roof, well, you can assume that the roof won't have the same amount of snow as on the floor. And that's why they came up with this, okay? Because the roof allows heating from the building to be lost. It can melt the snow a bit and all that. So over time, over the winter period, because of that heat loss, because of that melting of the snow, you can expect to only have about 80% of that ground snow load to still stay on the roof. That's how they came up with the CB value. Now, the CW, okay, CW is 1.0. Now, I can tell you that for normal buildings, guys, if you want, for normal buildings, you can also have a case where CW, you can use 0.7. But I don't recommend you ever using that. And this is only for normal or low. Okay, you can't use it for schools. You can't use it for, high or post-disaster. And if you use this, what the code says is that you have to expect that your building is going to remain in that condition within the life expectancy. In other words, within the 60 to 7 years that the building is going to be on, you're always going to expect that the wind's going to be able to rely on this. So I do not recommend you ever using that. So if ever you go in the building codes, why didn't you ever mention this? Because this here is a sweeping factor. You know that the wind will sweep some of the snow off the roof, and therefore you can reduce the snow load on your roof. Okay, so what happens here, so this is my this is my roof here. Okay, this is my roof here, and then here's my snow on the roof. The wind blows, and of course some of it can fall off. Okay, and therefore they allow you to sort of say 0.7. Now, great. What happens if you build this building and then the guy decides to plant trees next to your building? After 20 years, the trees obstruct this, and all of a sudden you don't have this situation anymore, and the snow starts to accumulate and the thing collapses. It becomes your problem. That's why I never bother using this value in my design. I never use it in my career, even though it's been around since I've been practicing. It's still around, but now the code is being very, very specific. It says, if you're going to use 0.7, make sure that it's there for the rest of the life of the building. So I do not recommend you use this. Always use 1.0. This for the wind, understand? The wind factor that can sweep so don't ever use that. That is not a good way to go. Now, this I do use because I know that if I put a slope on my roof, okay, if I know I put a slope on my roof, that it's going to stay like that unless the roof collapses. That means I've underestimated my loads. Or people have let the snow accumulate beyond the design load, and they're stupid because they don't realize that every roof has a certain limit. And when you get up to about 4 feet of snow, you should go up there, even though it's been designed for 4 feet of snow, to remove the snow. Anyways, that's another thing. So in other words, if I have a flat roof, right? In other words, if the angle of my roof starts to exceed like 30 degrees, okay, then you can take advantage of this. Otherwise, if you want to calculate what the CS value is, okay, so in other words, from 70 minus 30, and that's how you can calculate the CS value. So if I happen to have, I'll have an example where we're going to use this. So if I happen to have a 45-degree angle here for my roof, I will put it here and I will calculate the value of CS. Instead of using 1, I'll use something smaller. Now, look what happens when, okay, now CS is 0 where the roof slope is greater than 70, okay? So that means that if I look at my equation, okay, if I look at my equation, I have S is equal to SS times CB times CW times CS. What happens if this is 0? What happens to my snow load? What happens when you multiply something by 0?
Becomes 0.
So therefore, that means that I have no load on my roof. Well, in that case, when the roof exceeds 70 degrees, okay, remember what we talked about last week, that the minimum roof load is 1 kPa. That is, we saw that on the table. I know you guys don't remember it. And that's where you have to apply at least 1 kPa so that when the workers go up here, they can safely work on the roof without it collapsing under their weight. Okay, so that's the minimum load that you design a roof for. So if ever I do my snow load calculation and it's less than 1.0 kPa, you should use 1.0 kPa minimum. Okay, so keep that in mind. Now, after that, you have CS for the slope, and then of course, oops, you have the CA. CA, they call it a shape factor. In my days, they call it an accumulation factor. That's why they have the A here, okay? And basically, CA is 1.0, where you don't think the snow is going to shape into any other form but a uniformly distributed load. That's what CA is about. So, except that were appropriate for shapes of the roof, it shall be other value to account for. So in other words, if you have this situation, your CA is no longer 1.0. So these are the situations, okay? Non-uniform snow loads on gables, arches, and curved roofs and domes. So believe it or not, guys, okay, just to make you understand, you might not realize this, but if I have a dome roof like this, okay, instead of assuming that the snow load is going to be uniform all the way across here like this, okay, what actually happens on a dome roof, believe it or not, okay, this is what happens on a dome roof. The snow can actually do this. In other words, it has a higher accumulation on this side. That's because I don't want to get into it. Okay, that's because of how the vortices and the wind. Okay, so therefore, and then so therefore, when you have, in other words, if I have a flat roof, not a problem. I will have a uniform distributed load. Okay, I'm sorry, a uniform load going across it, but depending on the shape of the roof, and therefore the CA is no longer 1.0. So that's for that situation. And now, increased snow loads in valleys. What's a valley? Well, it's very simple. I mean, you see them, you know, for example, I'll show you what a valley is, if you guys don't know what that is. In other words, here's a roof here, and then you have another roof. In other words, I have another roof in here like this, and all of a sudden there's a valley, you know, or you can have one roof, you know, sometimes you can have this, and therefore the snow that accumulates here is going to be greater than the snow that accumulates here. So you have to assume that they're going to have a higher load, okay, in these valleys, okay? So if your house only has like this, or your house has, you know, like a hip roof like this, don't worry about it. Then, but if all of a sudden there's two houses next to each other like this, and the snow, this is the valley, so the snow can accumulate there. So that, then you have to find out how can you assess the snow that can accumulate in there. So that's another situation. Oh, sorry. Increased non-uniform snow loads due to drifting onto roofs that is lower level than other parts of the roof and at a level, and this we're going to be talking about today, okay? Because this is 99% of the time, this can be very problematic because people don't take this into account. So you will learn how to do this today. So let's not, I'll go more into details on this one and show you how you modify or how you evaluate the CA value for that. This is, I find that this is very important, okay? And we'll talk about that today. And then after that, increased non-uniform snow loads on areas adjacent to roof projections such as penthouses, large chimneys, and equipment. So in other words, when you have a roof and you have these projections on the roof whereby like it's probably gonna, okay, so for example, if I have a flat roof here and I have a penthouse that comes out here on the flat roof, okay, this penthouse will allow the snow to accumulate more around the penthouse, and therefore I have to be able to calculate that additional accumulation, and therefore my CA value is going to change just for this area here, okay? That's what they're talking about there. And like if you have large equipment, you can have large air conditioning equipment, all around those things, you have to allow for an additional snow load. So that's what the shape factor is. The shape is no longer just a straight level of snow, the shape allows for a different accumulation, therefore the load will be heavier. And that's what we're going to try to do. So now, increases snow due to ice sliding from or melting from an adjacent roof. So here what they're saying is that if all of a sudden I have a roof made like this, and then I have another roof here beside it, and the snow from this roof can slide onto this roof, and therefore you have to worry about how much snow is going to slide off and build up on this roof. That's what this is. This is very different from this one because this one here is simply a flat roof like this, and then there's a smaller roof next to it, and that's just the snow. So that's why this one is different. So this one is for when the roof has a slope and there's another building next to it, and the roof can slide off and accumulate onto the other roof. So that's, okay, so we will talk about this, especially for this case here, because I found that this case here has been very problematic in our practices because people don't realize this and it's overlooked and it always causes problems. So I want you guys to be aware of it. So, okay. Now that we have, okay, so now that we have all the, now that we have, well, we had an overview of all the variables that we'll apply this to an example, okay? We'll apply this to an example, and then we'll be able to sort of determine what the snow load is on that, or what would the snow load be for that building if we would ever be designing the roof of that building, okay? So here, example number one, I say that a school in Quebec City has a flat roof, okay, which is nice, and the foot perimeter of the building measures 70 feet by 100 feet. I'm sorry, 70 meters by 170 feet by 100, 70 meters by 100 meters. So this is school, okay? And you want to determine, and it's located in Quebec City, and you want to determine what is going to be the snow load that you will use to design the structure of the roof, and of course, everything else that is subjected to that snow load, the columns, the footings, and everything else, okay? So now, this is the way I always start. I always start by putting down the equation. So by putting down the equation, I know what are the variables that I need to establish. Okay, so therefore I write the equation. The snow load is IS, the importance factor, times the ground snow load, times all of the other factors, and then the associated rain. Now, of course, here we said that we're looking at a school. We know that that is high, and therefore right away IS becomes 1.15, okay? And that becomes the value of IS. So that's the first thing I worry about. Like I said, I never, and guys, I never use this, okay? I will only use this as a minimum, and then I would use this and use this depending on if it's not a normal building. So there we go. Okay, so now I have my IS value. So I took the first one. Now I look for my other two variables in here. And of course, this is straight from the tables in the National Building Code. So the SS, the ground snow load, and the associated rain, of course, I go here. Okay, so where am I? I am in Quebec. We said we were in Quebec. So, oh, sorry. So we are in Quebec. Now here, even in Quebec, just like Montreal, I don't know if you guys are familiar with Quebec City, but Sainte-Foy is like a suburb of Quebec City. Silly, Lévis, these are all suburbs, Ancien Lorette. So these are all within the region of Quebec City. So we're going to just take Quebec here. Okay, we're going to go across and we're going to look at the ground snow load and associated rain. So here's the ground snow load. And therefore, there's the value of SS and of course the associated rain. Okay, SR. So that's where I get my, and of course, be careful about the units here. This is in KPA. Okay, so for Quebec, they recommend that you take the ground snow load of being 3.6 kPa and the associated rain load of 0.6 kPa. So that's where I get those values from. And if ever you're in Quebec City and you don't know what region you're at, just be conservative. Take the highest one. So like here, for example, I would take 3.6. That's it. Okay, so that's where I get my SS value of 3.6 and my SR value. Now, CB. Now, like I said, CB is 0.8, or you have to check to see if it's going to get modified to being greater than 0.8 based on this characteristic length, right? Now, we said that this building measures W is the shorter dimension, okay, and L is a longer dimension, so that's it. And therefore, if I put this here, you see that when I work out this formula, I happen to have it's greater than 70, and therefore the CB value will no longer be 0.8. It will be greater than 0.8, and therefore I'm going to have to I have to calculate the value of CB in this case, and therefore this is the equation that I have to calculate the value of CB. It's 1 minus 30 divided by 90 squared, and therefore my CB value went up from 0.8 to 0.891. Okay, guys, 3 decimal places is ample. Even if you bring it to 2 decimal places, it's accurate enough. It's up to you. But 0.89 or 0.891, okay? And if you want to be ultra conservative, bring it up to 0.9, even better, okay? Putting more doesn't hurt. It only makes your client pay for a little bit more money. Putting less might hurt you. So there is my CB value, because the characteristic length, in other words, this is considered to be a very large roof. And what that means is that this roof is so large, okay, that this is the roof here, okay? This roof is so large, it's almost like when you look at snow in a field, right? What happens is that instead of having a nice uniform load, it's possible that you're going to have like these little things building up because it's such a big thing. And to account for that here, to account for that buildup here, even though it's a flat roof, there's no obstruction, that's what the CB value does on big roofs. When it's not that big, well, they found that in theory, when the roof is not that big, they find that the snow load is fairly uniform. But when it gets big, like, so if ever you guys go out and you drive and you just look out on the field and you see that there's kind of like little bumps that occur in the field, well, those little bumps can actually occur up on a big roof, and therefore to calculate how much more that bump is going to weigh on the roof, that's what the CB value is all about, okay? Now, once you calculate your CB value, of course, CW, first of all, when it comes to schools, any high or post-disastrous, there is nothing, you can't use anything less than 1.0. That's required by code. So right away, my wind exposure factor here, CW, is 1.0. Now, I've got a flat roof. Therefore, I know that under 30 degrees, I got to use 1.0. I can't take advantage of the fact that I have a slope. And then, of course, I have a flat roof. I have no obstructions on the roof, and so on and so on. And therefore, my shape factor ends up being 1.0. So now I've got all the values of every factor or variable in this equation. And I simply have to put everything in here. And I end up getting a snow load of 4.38 kPa. So what does that mean? Is that here's my roof here. Here's my roof. Oh, sorry, I'm drawing a little crooked. Here's my roof, okay? And of course, okay, so right here, I would assume that the snow is, well, somewhat uniform, okay, but it's a big roof, and I would have to design the whole thing for a load of 4.38 kPa. So that would be the load that I would impose on my roof structure and, of course, on the frame of my building. Is that, I don't find that this is, for me, I don't find it very complicated, guys. It's very simple. I've been doing it for 40 years. Does anybody have any questions? Or is anybody not clear on how to do this? Is everything okay, guys?
Yep.
Thank you, Emmanuel. I'm glad to hear. Anybody else have any problems? Guys, don't be shy, guys. This is the time to ask. I mean, we've got lots of time before it's all good. Can you guys give me a thumbs up next to your name so I can see that you're listening? Or thank you, Olivier. Thank you. It's nice to see a face to a name. Thank you. Okay, great. Okay, so guys, like I said, this is the first time around, and I don't find these things are very, very complicated. If you understand the reasoning behind it and you understand what your actual, I mean, like, I don't have a problem. But okay, so that was one example where we had a flat roof, and of course the importance factor was more than one, and of course we had the we had the fact that the CB, since it was considered to be a very big roof, the CB value changed from 0.8 and became bigger. Now I'm going to have another example for you. Okay, so here's another example. I try to bring in some examples so we can apply all the different, excuse me, we can apply all the different, whatchamacallit. Now, a fire station in Montreal has a 45-degree slope roof, and the footprint of the building measures 15 by 30. Okay, determine a snow load. So it's, we're going to be in Montreal. Okay, the architect decided to put a nice pitched roof on this fire station. I don't know why, I guess for architectural reasons. And this is the size of the building. Okay, so here, what we're going to do now, of course, the same thing as we determine the snow load. Now, so like I said, whenever I do these calculations, I write this equation. Of course, I know this equation by heart. I mean, but if you don't remember it, you simply open up the National Building Code, you go under the snow load. In other words, you go into Part 4 of the National Building Code. That's where you'll find this equation. And then we will start, you understand? So again, if you remember that for a fire station, you can appreciate it's a post-disaster building. I didn't bother bringing up the table because, we've seen it a couple of times. So for a post-disaster building, like a fire station, the importance factor is 1.25. And therefore, any snow load that we have, we're going to be putting 25% more than what we actually would calculate for a normal building. Now, as far as SS and SR go, well, I go to I go to Appendix C, right? Okay, so I go to Appendix C, and of course, let me make this a little wider so you guys can see it. So here we are in Montreal. Okay, so we're in Montreal, and it's good that you guys know what Montreal is. So we're in Montreal, and I have this thing in my way here, these menus. So here we are in Montreal. And of course, here's the ground snow load and the associated, okay? So, and what I'm going to do is say that the ground snow load factor is 2.6 kPa and the associated rain load SR is 0.4. And again, be careful about the units. It's all in kPa, okay? So that's where I get that information. And guys, the only time that you have to worry about in Montreal that the snow load is higher than 2.6 kPa is if you're in the east end of Montreal, you see it goes up to 2.7. And if you happen to be in Outremont, it's 2.8. So now you can appreciate how the mountain has an effect on snow loads. And therefore, that's why in Outremont, the snow load is even higher than anywhere else on the island, okay? So that's Montreal. So now we can clear this. We can minimize this. Okay, so I got my 2.6 kPa for my ground snow load and my 0.4 kPa for my associated rain. Now, CB, well, I'll do the calculation just to make sure that my characteristic length stays below 70. And in this case, the characteristic length is only 22.5 meters. And therefore, the minimum value of CB is 0.8. And therefore, CB stays to 0.8. The only time CB is never less than 0.8. The only time CB will be greater than 0.8 is when this value here, when the characteristic length is greater than 70. Otherwise, CB is always equal to 0.8, okay? And if you accidentally get a characteristic length less than, and you happen to put in that formula that we had in the other example, it's wrong, okay? You shouldn't be doing that. I never tried it, but some people. Now, so now the next thing is CW. Because it's a fire station, like I said, anything that's high or post-disaster, CW has to be equal to 1.0 according to the National Building Code. So that's 1.0. I don't take into consideration that the wind can be swept off the roof. Now, CS is a slope factor. So let's see what happens here. Now I've got 45 degrees, which is greater than 30. Therefore, I can take advantage that because of the slope, it's going to reduce some of the snow that can build up on the roof. And therefore, I will use the equation 70 minus 45 divided by 40. And that becomes the value of CS. So you see, instead of using 1 for a flat roof, I can go down to 6.25 for 45 degrees. And of course, if you put 30 in here, what happens? 70 minus 30 is 40, divided by 40, you get 1. So from 0 to 30 degrees, you use 1. As soon as you slope the roof slope over 30 degrees up to 70 degrees, you can diminish the value of CS. After 70 degrees, it becomes negative, which means it's 0. And therefore, you should be using 1 kPa. Now, as far as the accumulation factor goes, well, we're going to be using 1.0. And because we have nothing that affects the shape, and therefore we just plug in all the numbers, and we end up with a snow load of 2.13 kPa. Now, the interesting thing about this is that this snow load, okay, I'm going to show you here, okay, this snow load of this is my roof here at 45 degrees. This is my fire station here, okay. Well, believe it or not, this 2.13 kPa gets applied this way, what they call global horizontally, like this. This is how you apply the load to your roof. And don't worry, ADA, the software, it actually was able to put that in, and you do not apply the load this way. Okay, that is wrong. You apply the load as if it's acting horizontally across the roof, and that's how you would apply the load to your structure. Okay, so that's just to let you know. Okay, so clear the drawings. And then, okay, now I want to talk about something really interesting. Okay, what happens, and I love this because I've seen many situations where people have overlooked this and it's caused nothing but problems. So what happens when, let me ask you a question. I have a roof here like this, and I have a lower roof right next to the building like this. What do you think is going to happen to this roof here when it snows and the wind is blowing? What do you think is going to happen to this roof here?
It's going to have more snow.
Yeah, exactly. Perfect. Yeah. In other words, I agree. Now, everybody understands? In other words, if the snow builds up here, okay, and the wind is blowing like this, well, the snow is going to drift off and build up on this roof here. Everybody sees that? Okay. Therefore, you have to be able to calculate how much snow can build up there because of the snow blowing off this roof here onto this roof here. And that's what we're going to learn how to do. And how do we account for this? This becomes the CA factor for this roof. Okay, so we will do that. So now, the load distribution on lower roof adjacent to high roof is taken as a triangular shape as illustrated in figure G5. Now this is figure G5, okay? This is figure G5. Now guys, I'm sorry, I have all these menus in the way here. Okay, so here, what they're showing you is that here's the upper roof. Here's the upper roof. Here's the lower roof. Don't worry about this. It means if you have a lower roof that has a slope, you can take advantage that if it's over 30 degrees, you can reduce the snow. So what's happening here is if this roof here is more than 5 meters away from that roof there, then you don't have to worry about it. In other words, if the distance here is more than 5 meters, okay, then you don't have to worry about it because any snow that falls off the roof will just simply fall here. But if this building is closer than 5 meters, well, you'll have to worry about the possible accumulation of snow. Okay, so if your building happens to fall right here, let's say at 2 meters away, well, then you would calculate as if it's against it and take the values right at 2 meters away. So that's what you do. Okay, now don't worry about this. This is all okay. And these are the formulas that we're going to be using. Okay, so this is what they mean by you have to be able to calculate how much of a drift can accumulate onto a lower roof caused by all the snow that can be falling on the upper roof and so on. So that's what we're going to learn how to do. Oh, sorry. Okay, so CA decreases linearly with a distance x from the step of the roof, okay, beginning at CAO at x equals 0 to the tail end. So here what they're trying to make you understand is that if you go back to this figure here, where am I? Okay, so this, in other words, this is the value. When you calculate this value, it would give you the value of the snow load right there. Okay, when you calculate the value of CA at O, what they're meaning is that the distance here is x is equal to 0. And that's what they mean, that you're actually, from this is CAO right there. And then after that, you can assume it to be a linear over a distance here of xd. And what's that distance? Well, that's how you calculate the distance, xd, and we'll learn how to calculate that distance. So that's what they mean that by that statement. Okay. And CAO shall be taken the lesser of. So there's two ways of calculating CAO. Here's one equation. CAO, in other words, the value of the accumulation at the face, right where the upper roof meets the lower roof, the CA value is the unit weight times the height times the you saw what CB was, and you know what SS was. So that's one equation. And then you have CAO is equal to F divided by CB. There's another equation. So you have to calculate both, and you take the smaller of the two. Okay. Now, does anybody want to know why there's two equations? Is anybody, nobody's curious to know why should there be two equations instead of just one?
Sir?
Yes.
Is it because the snow from the upper roof accumulating?
No, it's good. No, okay. The reason why we have two equations, okay, is that one equation is for the situation where you have an upper roof here and the lower roof is very close to it, okay, and the step gets filled in completely. And the other situation is that you have an upper roof here, you have a lower roof here, and the step will never get filled up completely, and therefore you'll only get this amount of snow. That's why you have two equations. One is to account for when the step gets filled up completely, and the other one is when the step will never get filled up, no matter what. So that's why we have two equations. Okay. Now, so the unit weight of the specified unit weight of snow is, now guys, 3.0 is an average unit weight, okay? I don't know if you guys can appreciate this, but 3.0 kilonewtons per cubic meter, excuse me, that's, you know, when the snow falls down on the ground, you know, when you see that nice fluffy snow falling to the ground, well, believe it or not, that weighs about 0.5 kilonewtons per cubic meter. And then once the snow gets onto the ground, it starts to crystallize, it starts to, you know, get more dense and everything else. So this is not the actual weight of snow. This is like a good value of snow. There are areas in Canada where the unit weight of snow can go up to 4.5 kilonewtons per cubic meter, where it's very, very moist and the snow is heavier, and therefore you should be using the value in that area. But here in Quebec, this 3.0 is a good number to use, and therefore we've been using 3.0 in our calculations. And of course, H is the difference in height between the lower roof and the top parapet of the upper roof. Who doesn't know what a parapet is? Please let me know and I'll explain it.
Can you please explain?
Okay. Like architects, what they do, architects, when they build flat roofs, okay? When they build flat roofs, okay, they kind of build a small wall around the perimeter of the building. This could be about, 10 inches, 10 inches. It can be like 30 centimeters, 40 centimeters. But anyways, so they build a small wall. And if I look at the cross section here, okay, if I look at the cross section here, this is what it looks like. So here's the outside face of the wall. There's the parapet. There's the roof. There's the parapet. And the reason why the architects do this is because they want to create a basin so that they can drain the water to the roof drain and that it doesn't spill over onto the sides of the wall. So those are parapets. Now, if I go back to here, that's what they're showing you here. This is the parapet right there. Okay, so that's what the architect builds. In other words, like you never, on a flat roof, you will never see this. Okay, very rarely, unless it's a very cheap industrial building and the architect really doesn't care the water spills over on his walls. But any decent building, the architect will always have a parapet. So when you're calculating the value of H, you do not take it from the height of the upper roof to the height of the lower roof. You take it from the height of the parapet to the height of the lower roof. Okay, that's what they're saying. Now, CB is a basic snow factor. And guys, keep in mind, this is a CB of the lower roof, okay, not of the upper roof in this case here. Okay, so when you're putting it in this equation and this equation, you're using the CB of the lower roof. Okay, so keep that in mind. Okay. And of course, SS, we saw what that is. That's the ground snow load that occurs within in a probability of 1 every 50 years. Okay. Now, F is taken as the greater of. So you got to take the higher of the two. So F can be as simple as 0.2, or this is the ugly equation to calculate F. And in most cases, this is the one that governs. Okay. So therefore, be very careful when you use this equation because this F value gets used, okay, for other reasons. So therefore, if I do this F calculation, I end up getting 1.83. I have to use 2. I can't use anything less than 1.83. And if you want, if this thing happens to exceed 5, you can stop at 5, but I won't influence you on there. Now, we said that here that gamma is the unit weight of snow. LC, we know what that is, but LC is the characteristic length of the upper roof. Okay, so make sure you calculate the characteristic length of the upper roof. And that makes sense because I want to know like how much snow can be on the upper roof that can drift onto the lower roof. Okay, so that's why I need to calculate the characteristic length of the upper roof. So if the upper roof is really, really big, well, it's going to affect the CB value. And then, of course, this is the equation to calculate the characteristic length. We saw that before. Now, we know what SS is. We get that from the table. HP is the height of the parapet. So remember, okay? So you will go to the architectural drawings. You would see if the architect sent you his drawings, he would show you that here. Architects will always tell you how high they make their parapets. Okay, I've been involved in buildings where the architect made this parapet. You know, he made this 1.2 meters high for architectural reasons. Okay, so the parapet can be as high as 1.2, and don't forget that when you calculate the height, it goes from there to there. Okay, that's what you're calculating, from the height of the parapet to the height of the lower roof. So that's the height of the parapet. And CB, the basic roof snow load factor of the lower roof always, okay? So this is the characteristic of the upper roof, and CB is for the lower roof. So you've calculated that before. You can just use that value. and the length of the drift. In other words, how much can the water, like for example, once you've calculated this, and how far should you assume that this drift is going to occur? In other words, that distance away from where the upper roof meets the lower roof. So in other words, here's the upper roof, here's the lower roof. Okay, you're calculating the load here at where it occurs right next to it, and you want to know how far should this go down. Well, this becomes the XD value. And therefore, to calculate that distance, you have two equations. Okay, you have two equations to calculate that. You have XD is equal to the height that you used before, the same height that you had here, okay, from before. And the same values here, or XD is equal to, this is the F that you calculated here, and that's why it's important that you calculate correctly, because you're going to be using it again in here. And you take the lesser of these two. In other words, if one gives you 22 meters and the other one gives you 12 meters, well, the drift is going to be over 12 meters, not 22 meters, okay? So this is when the step gets filled in, and this one the step does not get filled in. So that's why you have two equations. And if guys, to give you an idea, this gives you about a slope of 1 in 5. So in other words, for every 1 foot of difference in height of the building, it probably is going to go out about 5 meters in the other direction. So that's approximately the slope that the drift, these things give you, okay? Okay, so now we've got all of these, and what we're going to do is, of course, we're going to apply it to an example so that we can, make sure we know how to use this properly. And so here we go. So we calculate the snow load. Okay, calculate the snow load for the upper and lower roofs for the hospital located in Louisville, Quebec. Show your results on a sketch. And this is what I'm going to expect you to do after you do these calculations, okay? So here, I didn't bother putting a parapet here because most likely there would be a parapet here also. So I just didn't want to confuse you. So here, in this case here, the architect came up with, okay? So here's the L for the upper roof. And of course, the W for the lower roof is the same as this one, okay? So here's the upper roof. This one's 40 meters high. This is 30 meters high. And therefore, this should give you what the H is. Okay, so you don't take the H from here, you take the H from there. Okay. And now, so what we're going to do is that we're going to start calculating all the values for the upper roof, the uniform snow load up for the upper roof. And then whatever is good for this, assuming that the CB value hasn't changed, then it can also be good for the lower roof. And then we're going to go and calculate what the accumulation factor is in between the two. Okay. So that's what we're actually going to be doing. So we start. So we start with the upper roof. The upper roof, we say that S is equal to IS, SS, the same thing that we did before. It's almost assuming that the building is all by itself. There's nothing. And as a matter of fact, that's what is actually happening. That building will not be affected by the lower roof. Okay. And therefore, I know that I'm designing a hospital. Therefore, the importance factor is 1.25. Okay. Now, SS and SR. Well, if I come here, now, if I go to, I'm going to go look for Louisville. Of course, it's in alphabetical order. So where is Louisville? Here's Louisville. So I'm going to go across. Okay. And therefore, the SS value and the SSRR value are right here. So I have 2.9 for the ground snow load and 0.4 for the associated load, and of course in KPA. So that's where I get the values for Louisville. And guys, when I go to the National Building Code and I look for these values, I take my ruler and I put right across here to make sure that I don't accidentally take 2.3 instead of 2.9. You understand? I try to be very careful, and I even sometimes double check to make sure I'm using the right values. So, be careful about that because it's so easy for you. Oh, Louisville. Oh, okay, Louisville. Oh, Louisville, 2.3. Okay, because you're just going across with your finger. And so be careful about that, Okay, so we have 2.9 for SS, and of course it's the same SS for the lower roof, and the SR is the same for the lower roof, 2.4. Now, CW, I calculate the characteristic length of the upper roof, okay? which I'm going to be using later on, but the characteristic length of the upper roof here happens to be less than 70. Therefore, I know that the CB value is 0.8, okay? So therefore, I will not use anything less than 0.8. The wind exposure factor, because it's a hospital, I have no choice to use 1.0. Because it's a flat roof, what is the value of CS? 1.0, because it's a flat roof. And of course, the CA, there's nothing that's going to cause the snow to form a different shape. It's going to be considered to be fairly uniform, you know, like fairly straight across the whole roof area. And therefore, the CA value for the upper roof will be 1.0, okay? So now that I've got all my values, I will go ahead and calculate what the snow load is on the upper roof, and I put it all into my equation, and I end up getting 3.4 kPa. So now what's happening is this. I happen to have, okay, so here I have my roof, my upper roof, okay, and I just finished calculating the snow load here, and as far as the snow load goes up here, it's going to be 3.4 kPa. Now, for the lower roof here, okay, for the lower roof, if the CB value does not change, right, if the CB value doesn't change, you notice that everything else in the equation is the same. So for the lower roof here, even here, for most of the roof, it can be 3.4 kPa. Now, the only thing I have to worry about is that when the snow drifts off this roof onto the lower roof, how much is going to accumulate in this area of the roof? So therefore, that's where I have to calculate that CA, right? And that's what they call a zero, where in other words, when the distance where the lower roof meets the upper roof, to be able to calculate the value of the snow there and assume that I can go down to a linear up to this value here. So now, for the lower roof, I have the same equation, but now I'm going to calculate the accumulation factor right where the lower roof meets the upper roof. Now, the same importance factor, the same ground snow load, the same associated rain. Now, you notice that the characteristic length is less than 70, therefore CB is 0.8. That doesn't change. And the wind exposure factor is 1.0. As a matter of fact, it should be 1.0 because it's the fact that it's a hospital. But on top of that, you have a building obstructing the snow from blowing off. And then, of course, it's a flat roof, 1.0. Now we're going to get into calculating the CAO. In other words, what is the accumulation or the shape factor of how much snow can accumulate right where the upper roof meets the lower roof, okay? That's what we're trying to do. And that's how this factor will change the value of the snow load right at that point. So what we're saying is that here's the upper roof, here's the lower roof, okay? I know that I'm going to end up with some kind of load that looks like this. Here, believe it or not, is the same value as here because, okay, I just want to be able to calculate what's the value right there. In other words, where X is equal to 0, okay? That's what they mean by XO, okay? How much of a load do I have there? And that's what this factor will allow me to that's what this factor does. It gives me the value that I have to put in an equation to calculate the value right there. So now, CAO is taking the lesser of. Remember I told you there's two equations, one where the step gets filled in, where the step doesn't get filled in. So therefore I have to check both. So here's one equation, the unit weight of snow times the height, which is the height from the roof, from the parapet of the upper roof to the level of the lower roof. And of course, these we have. And then this is for the other one where F has either, okay? We saw the equations. Now, I do the first one. I put in the values. The unit weight of snow, I take it as 3.0 kilonewtons per cubic meter. Now, H is 10 meters. I don't know if you guys remember, but if you go back to the sketch, I said one was 40 meters, the other one was 30 meters. Therefore, from the height of the parapet, there's a 10-meter height difference between the upper roof and the lower roof. Now, the CB, excuse me, the CB doesn't change in this case because whether it's the upper roof and the lower roof, they're both 0.8, but this should be the CB of the lower roof, which is 0.8. And of course, SS is the same whether it's the upper roof or the lower roof. That's the ground snow load, and that's 2.9. So I do the calculation here, and I end up with 12.93, okay? So in other words, I would take all my snow load and multiply by 12.93 if this is the one that governed. So that's one, and I have to take the lesser of. Remember that, the lesser of. So now I go calculate this side, this equation. So for this equation, now for the lower roof, I take the accumulation factor where the lower roof meets the upper roof. I have F divided by CB, and the CB is the CB of the lower roof. But like I said, in this case, they're both the same, 0.8. Now, F is taken as the greater of. So you got to take the higher of the two values. So F is either equal to 2 or F is equal to this equation here. Now, guys, okay, and don't forget, this is CB of the lower roof. And again, I'm going to repeat myself. It does not change because they're both one and the same for the upper and lower roof. Now, guys, when you do this equation, okay, I've seen this year after year. Okay, this is where most people make their mistakes. Okay, take your time, do what's in the brackets. Then, like for example, do this value here, square it, then multiply it by 6, then do this value here, then do the square root of this value, then multiply it by 0.35, and then add the CB value to it. I mean, this is where I see people doing the classic mistake year after year when they're doing these snow loads, okay? So now, remember that this is the characteristic length of the upper roof. We've already calculated that, so we don't have to recalculate it, okay? So if I put in all the values correctly, okay, guys, so we'll go through it. Remember that this is just a coefficient here, 0.35. So the unit weight of snow is assumed to be 3.0 kilonewtons per cubic meter, okay? If you remember, we calculated this before because we calculated the characteristic length of the upper roof. This is for the upper roof, okay, not the lower roof. So I used the characteristic length of the upper roof. And we did that already when we wanted to calculate the CB value. And of course, this we got from the table, okay? Now, again, the unit weight of snow, okay? Now, HP, of course, you see on the drawing, you go look at the architect and you look at how high is this parapet, and that's the HP value. And if you look at the sketch, I gave you a value of 16-inch parapet, which is reasonable. Okay, parapets are never less than 10 inches, and they, on the average, are about 12 inches, and they can go up to 16. They can go up to whatever the architect wants to do. That's my HP value. Now, guys, to give you an appreciation why this becomes a factor, okay, so that you guys can appreciate why they put this into the formula. If I have a roof here like this, and I have a parapet that's this big, okay, and I have my lower roof here, and I have the same building, okay, I have the same building, but the parapets are much higher, okay. Why does a parapet have an influence on how much drift can do? Because the snow has to build up to here before it can start drifting onto the lower roof. So the higher the parapet, the more likely there's going to be less snow drifting onto the lower roof, and that's where this is taken into account in these equations. That's where the HP becomes important. So for example, if this is like 4 meters high, most likely it's going to be 0 accumulation because it's all going to stay on this roof. Okay, so that's where the parapet it becomes. That's why they have this in the equation here. And then after that, of course, again, the ground snow load. Okay, then of course this whole thing, you take the square root of it. Once you take in the square root of it, you multiply by 0.35, and then you add the ground snow load, the CB value to that. Okay. So we do that equation and we end up with 3.2. And of course, it's greater than 2.0. Therefore, I use this value here because I use the greater of. If I happen to end up a value here of 1.8 or 1.9 or 1.98, I would use 2 minimum, 3.2. And guys, just to make you understand is that the range of F, this should be somewhere between 2 to 5. Okay, so if you start getting values like 32 for F, you made a serious mistake. Okay, so this should be in the range. This is the range that you should have for the F value from 2 to 5, okay? And that's, if you happen to get 15 for F, you did something wrong here. I've never seen 15 in my life, okay? To give you a sensitivity of what range you should be in case you're doing this calculation. Now, I put this down, the CB, I end up with 4.0. And of course, I got to take the lesser of the two. The other one was 12, this one is 4. Therefore, this is the one that's going to govern my design. So that means that since this is the smaller one, the roofs are so high, the step will never get full. And therefore, I only have to go up to a certain level that the step will go up to because of the drifting of the upper roof. That's what this means. So in this case here, it's not filled in by the upper roof. It will not go up to the ever go up to the upper roof. Now I've got that, so I go ahead and put that in my equation. Now you notice here, instead of using 1, I'm using the value of 4. Like in other words, this is where this here, this factor goes right there. So instead of having 1.0 when it's uniform, I increase it by 4 times that, and then of course add the associated rain. And therefore I end up with 12.1 kPa. So what does that mean? That means that right where the upper roof, and the lower roof meet, okay? That snow accumulation there, right there, that value right there where X is equal to 0 is going to be 12.1 kPa. In other words, it's going to be 253 pounds square foot of snow that can build up right there. Now, when does it come back down to that uniform? Well, that's going to be the value of XD, okay? And that's what we're going to calculate next. So that's what that means. So here we have a uniform load. Here we have a uniform load. And now we're going to go calculate when does this thing come back down to this level here so I can consider it to be uniform down here again. And that's what we're going to be calculating. So we have XD is going to be the smaller of these two, okay? And then here again, guys, the classic mistake I see every year, people do multiply H by 5 and then they subtract this from it, or I don't know what they do, but I can tell you that instead of working what's in the brackets first and then multiplying by 5, I've seen that mistake over and over again. So be careful on when you're, okay? So therefore, I'm going to calculate here. I calculate 5. Now H is the same H that we've used up here, the 10 meters, okay? That we used, oh no, 10 meters was, yeah, we didn't use it in this equation. H was 10 meters, the difference between the two roofs. And then of course, CB is the CB of the lower roof. Again, the same as the upper roof. SS doesn't change, this doesn't change. And therefore I end up getting 46.1 meters. So I don't know if you guys can appreciate that, but that's one hell of a length, you know, 46.1 meters, okay? Or XD is equal to this one here, where you take the unit weight of snow divided, I'm sorry, you take the ground snow load divided by the unit weight of snow. And that's where the F factor becomes important again, because you're using it again in this equation. Make a mistake there, you repeat the mistake here. And of course here they want you to subtract the snow load factor of the lower roof, always, okay? And I end up with 11.6, and that's reasonable. In other words, you take the lesser of the two, and therefore that's what it's going to drift off to, okay? So if now I take all this information and I want to show somebody what we're going to be using in order to design my roof, I take all of this, and of course this is the one that governs, this the lesser of the two. So that means that I went ahead and I calculated all my loads for my upper roof. I'm sorry, I should have done a little bit better. My upper roof, I calculated the ones for the lower roof. I calculated the value where it would be the maximum value here based on this equation here. And then I calculate how far that is going to drift away. And we calculated that to be 11.6 meters. And then the snow becomes, again, uniform for the rest of the roof. So this uniform here is the same as up here. And all I did now is calculate the value that it can eventually be. Now, guys, to give you an idea of, are these equations, are they like, I was involved in a matter where a roof had collapsed, okay? When I use this equation and I end up getting a snow load of 290, I remember I used this, I ended up getting a snow load of 295 kPa. Not kPa, sorry, this is impossible. PSF, okay? That's what I got from this equation. And when the guys went to measure the snow load on the roof after it collapsed and they did the calculation, the snow load that had accumulated between the upper and lower roof was about 293 PSF. So just to give you an idea that this thing is pretty accurate, okay? So, okay, so there you go. So now I've got all the information in order to show this all on a sketch. And here's a sketch, okay? So this is what happens. So on the upper roof, I will have a snow load of 3.4 kPa. On the lower roof, okay, on the lower roof, I will also have a value of 3.4 kPa. So in other words, on the lower roof and on the upper roof, I will have a value of 3.4 kPa. The only thing is that because, so Yavor, are you talking to me? Sorry.
Oh, no.
Okay, because I heard
Sorry.
something. No, it's no problem, no problem. I thought you were talking to me.
I don't know why it's muted.
Well, there you go. I muted you, so no problem. So basically, both the upper and the lower roof have 3.4, but the problem is that because the snow can drift onto the lower roof here, okay, if the snow can drift onto the lower roof, then what's going to be the value of the snow right where the upper roof meets the lower roof? And that's where the CAO, in other words, where X, the X distance here, the XD value here is equal to 0. That's where you calculate that factor. That's going to give you the value right there, because that's the only thing that changes in the equation. And then you want to know how long is this drift going to be, and that's where you calculate that XD value. And therefore, and then after that, you can assume it to still go back to be relatively straight. And guys, just to give you an idea, like, what is 12.1 kilonewtons per meter squared, right? Divided by 3.0 kilonewtons per meter cubed. Can somebody work this out for me? Tell me what that is.
I got 4.03.
Okay, about 4 meters. So in other words, if you ever look at this, the height of the snow on the roof that's going to be against, like at the end of the winter, it can be up to 4 meters high here. You understand? And if you want to, like I said, this is an approximation, okay? But if you want to know, like, for example, and that's why, guys, when you're, for example, if you're at home, okay, remember, for example, if I take Montreal, okay, I take Montreal, I know that SS is 2.6 kPa. I know that SR is 2.4 kPa. I know that CB, blah, blah, blah. And I do a snow load calculation in Montreal, okay? And I end up getting that the snow load calculation for Montreal is approximately, I'll tell you right now, 2.5 kPa. That's the average snow load that the buildings are designed for. So if I take 2.5 kPa divided by 3.0 kPa, what do I get in terms of height? I have about 0.83 meters. You guys agree?
Yeah.
Okay. So guys, when you start seeing about a meter of snow on your roof at your home, what should you tell your parents?
You should probably get rid of the snow.
Exactly. Okay, guys, and that's why. Okay, because remember, now the reason why I say 1 meter, because don't forget there's factors of safety, there's margins of safety that are built into the snow, into the design of the roof. Okay, but when you start seeing 3 feet, 4 feet of snow, you should tell your parents, or you should tell wherever you know, take the snow off your roof, because especially if you're not through the winter yet, or even if you're through the winter and all of a sudden it starts raining a lot and all that rain gets accumulated with the snow. Guys, this was back in 2008. We had a situation where we had over 400 millimeters of snow that year. And around the month of February, March, a lot of roofs were totally, overloaded, and we started having collapses. As a matter of fact, people have lost their lives because of that. And, even though like I said, even though the snow load, is that they give you to do these calculations is reasonable, but you never know what nature is going to throw at you. Okay. And therefore, when you start seeing snow loads over and above, okay, if you start seeing, especially Montreal, if you start seeing snow loads that are over 4 feet, in other words, about 1.2 meters, anything over a meter, and it's just January, it's going to keep on snowing until the end of March, maybe beginning of April. So the prudent thing to do is to go up and remove the snow. Okay. And unfortunately, a lot of people don't do that. And sometimes there's some dire consequences that occur because of the fact that people don't realize, because they just figure, it's designed for it. Yeah, it's designed up to a certain level. After that, you should take the snow off. Okay. So keep that in mind, please. Now, I think that's it for today. I'm not sure. I think that's the end. Yeah, okay. So you will be getting in about 45, or I don't know if you got already. I scheduled the assignments to be sent out to you by 11:45. Have you guys received the assignment yet? Has anybody checked?
No, I didn't see the assignment yet.
Well, it's because I scheduled it for 11:45. So, okay, so let me just put, let me stop sharing here. Let me put the